Welcome. I thought it might be instructive to go over the history of carbon dioxide, at least in recent years, to dispel some of the misinformation that has been put about by those that believe that carbon dioxide is not causing global warming. These are some of the questions that I intend to try and answer during this session. Why does atmospheric carbon dioxide concentration vary? How much has it changed in the recent past? How do volcanic eruptions affect carbon dioxide levels? And do ocean temperatures affect atmospheric carbon dioxide levels? One of the questions we could answer is, how did we get here? We're now above 420 parts per million. In fact, March of this year, our level got to 421 parts per million. That's an increase of 2.19 parts per million since the same time last year. So there's a steady build-up of carbon dioxide in the atmosphere. You can see it here. The red curve is the monthly average carbon dioxide, and that is the annual variability that I'll talk about a little bit later. But the black curve is the annual averaged carbon dioxide level, and you can see that that has been steadily climbing. However, there is some hope. If you look at the trend up until last year, there's a certain slope to that. However, since then, that slope seems to have lessened somewhat. So maybe we're beginning to make an impact on carbon dioxide levels in our atmosphere. Okay, let's take a look at this annual variability. Here is the last 2 years, and you can see that overall there's a general upward trend, but there's also this oscillation that occurs throughout the year, through the seasons. And this is caused by an asymmetry between the northern and southern hemispheres. The northern hemisphere has more land and therefore more plants than the southern hemisphere does. So therefore, when we're into spring and summer in the northern hemisphere, when they are putting on leaves and flowers, they absorb a lot of carbon dioxide from the atmosphere, and overall atmospheric levels of carbon dioxide fall. In the autumn, when the leaves drop and start to rot, that carbon dioxide is put back into the atmosphere. Now, because of the asymmetry between the two hemispheres, the level of growth in the southern hemisphere does not compensate for the level of decay in the northern hemisphere, so the carbon dioxide levels go back up again. One thing you can see here that we'll deal with more in a minute is that volcanic activity does not affect carbon dioxide significantly. Here we have the Tonga event, which was a VEI event of 5, which is a very large event, in January of 2022. And you can see that the level of carbon dioxide has hardly changed at all as a result of it, if indeed that was it. And after a couple of months, it's returned back to normal. So basically, even large volcanic eruptions have very little effect on the carbon dioxide level in the atmosphere. And we're going to talk a bit more about that too in a minute. Let's take a longer look. This is over the last 60 years. This is the so-called Keeling curve, which started in the late 50s. And you can see the annual variability there on the plot, this sort of sawtooth. Again, you can see the strong upward trend over that period. So we've seen carbon dioxide increasing steadily for the last 60 years. Let's take a look at the last 300 years, basically the time period of the Industrial Revolution. It started with a relatively slow rise in carbon dioxide over the first 100 years, just 5 parts per million. The next 100 years was a bit faster, at about 14 parts per million. Then we'll take 25-year increments. The next 25 years, then 1900 through 1925, added 8 parts per million. 25 to 50 added 9 parts per million. 1950 to 1975 added 15 parts per million. So you can see this is beginning to accelerate. 1975 to 2000 added 40 parts per million. And the last 23 years, not 25, note, has added another 50 parts per million. If we waited for 2025, that would be probably something like 55. So that's a 64% increase in the last 50 years, which is quite a stunning amount of activity releasing carbon dioxide. Now let's take a look at the modern era. So that's the last 2,000 years. And you can see for the first 1,700 years of that, there was basically no change. So all the rest of the increase has been in the last 300 years. And that basically is because of the Industrial Revolution. Next, let's take a look at the Holocene. That's the last 10,000 years. One of the things that's to note here is that the Holocene temperature maximum was about 8,000 years ago. And that actually represents a low point in the carbon dioxide level of the atmosphere. So that really says that ocean temperatures have very little effect on carbon dioxide because they would have been at their hottest back then and carbon dioxide was still very low. Over the next 6,000 years, the numbers only increased by about 15 parts per million, which is probably due to some minor land use changes. We started farming regularly, and also the beginning of industrialization with the Roman Empire, etc. If we look at the ice cores, we can go back as far as 800,000 years, and this is the levels of carbon dioxide that was in fact during that period. You can see that the highest point prior to the modern era was 300 parts per million, and most of the time it was much lower than that. In fact, it averaged between 300 parts per million and 170 parts per million. A note here that some people claim that once you get below 200 parts per million, all life dies. That's not obviously the case. Well, I did say we're going to talk more about volcanic eruptions, and the largest volcanic eruption in the modern era is Pinatubo. And you can see it here, it was in June of 1991. There's where the arrow is. The annual variation in carbon dioxide is shown with the blue curve. The annually average carbon dioxide is shown in the red curve. And you can see there's no particular feature associated with this massive eruption of the Mount Pinatubo. We can see that even major eruptions like Pinatubo do not affect carbon dioxide levels in the Earth's atmosphere. Another old favorite to say, well, the oceans are warming up and they're giving out carbon dioxide, and that's where this carbon dioxide is coming from. There's a number of reasons why that isn't so, but the one that they mainly use is water solubility. Carbon dioxide solubility in water drops as the temperature of the water increases. The curve is shown here. So if you start with some water at say 10 degrees centigrade and heat it to 30 degrees centigrade, the amount of carbon dioxide the water can hold drops quite significantly. Is this a problem? No, because this only occurs when the water is saturated with carbon dioxide and the seas are not. Let me show you on this curve how much carbon dioxide are already in the oceans. It's down here. So you'd actually basically have to boil the seawater to get the carbon dioxide to start outgassing. So the extra carbon dioxide is not coming from the ocean. And there are a number of other arguments that back this particular opinion up. One, ocean pH levels are falling, that's acidification. As the oceans absorb more carbon dioxide, they become more acidic. Now, if they were releasing more carbon dioxide than they're absorbing, then they become more basic. And that's not happening. They are absorbing more carbon dioxide than they're releasing. Also, the carbon isotopes in the atmosphere are changing. They're indicating that the carbon that's being added to the atmosphere is old carbon. And that is the sort of carbon that comes from fossil fuels. Carbon dioxide coming from the oceans would be new carbon because it would be fabricated by the living plants in the ocean. Another major clue is that the level of oxygen in the atmosphere is dropping. So remember your chemistry where carbon plus O2 equals CO2. So every atom of carbon you burn is one less molecule of oxygen for you to breathe. Lastly, you can do dead reckoning. The amount of carbon dioxide that's being added to the atmosphere exactly equals the amount of fossil fuels that we burn minus the amount that goes into the oceans and into the land. So it seems to be a pretty solid case that this carbon dioxide in the atmosphere is coming from the burning of fossil fuels. The last refuge of some of these deniers is that there's so little carbon dioxide in the atmosphere that it can't be doing very much. Carbon dioxide makes up only 0.04% of our atmosphere, and you would think that's not very important. Then you realize that only 0.0002% of body weight of cyanide will kill the average person. Now, most of our atmosphere, nitrogen, oxygen, and argon, play absolutely no role in energy transport, so have no effect on incoming solar radiation or outgoing infrared radiation. So it's only the active molecules that are involved in that. There is so much carbon dioxide in the atmosphere that only one IR photon in 1,125 million photons gets to escape from Earth directly. All the rest are scattered around. So a lot of that extra energy is brought back to the surface and heats the surface. One of the things you have to worry about is water vapor. Water vapor is what's called a secondary greenhouse gas, in that its concentration in the atmosphere depends on the temperature of the atmosphere. So it acts as an amplifier. If the temperature increases, more water vapor will be in the atmosphere and it will heat the atmosphere more. If the temperature drops in the atmosphere, water vapor will drop out of the atmosphere and the heating effect and the cooling effect will be increased. So what can we conclude from all of this? The extra carbon dioxide in the atmosphere is coming from the burning of fossil fuels. Volcanic emissions have a negligible effect. Oceans are still absorbing more carbon dioxide than they emit, so they're not producing that carbon dioxide. There's plenty of enough carbon dioxide in the atmosphere to explain the increased warming of our atmosphere. The Earth is at its highest level of carbon dioxide in millions of years and is rapidly making that tens of millions of years. And by 2100, carbon dioxide levels could be over 600 parts per million in our atmosphere, which I think would be disastrous. So thank you for listening, and until next time, stay safe and goodbye.